Hello everyone and welcome to this video. So while we're still on the topic of dynamics, now we are looking at more of some questions. So we've categorized them in a way that it makes it easier for you to digest. So now we'll do questions related to the ideas of mass flow rate. Let's start. So the first question is this one. Question 32, part A, state the principle of conservation of momentum. Again, very straightforward. It's the exact same marks as it would be asked for in O levels. And you know that each of the marks is for a certain statement. So we say in a closed system, or alternatively, you can also say that if no external forces act, both of these mean the same thing. Both of these the examiner accepts. So in a closed system, the total momentum remains constant. Now, alternatively, what you can also say here is that the total momentum before collision equals the total momentum after collision. That's also right. This is also right. This is just less words, so I like this one a bit more. All right, next. The propulsion system of a toy car consists of a propeller attached to an electric motor as illustrated in 3.1. So the car is on horizontal ground and is initially held at rest by its brakes. When the motor is switched on, it rotates the propeller so that air is propelled horizontally to the left. The density of the air is 1.3 kg per meter cube. Assume also that the air moves with a speed of 1.8 meter per second in a uniform cylinder of radius 0.045 meters. Also assume that the air to the right of the propeller is stationary. Show that in a time interval of 2 seconds, the mass of air propelled to the left is 0.03 kg. All right, so how do we go about doing this question? So when I see this, and this is what must click for me, is that I'm given the density of air, I'm given the speed of air, I am also given some radius from which I can find out the area, right? So this is a certain cylinder, this is a certain cylinder. So I need to find that the mass propelled to the left is 0.3 kg in this much time. So certain mass, certain time, this must give me the idea about the mass flow rate, right? So mass flow rate is given by the expression of rho AV, right? And mass flow rate is basically delta M over delta T, right? So first, if I find out the mass flow rate, which is rho AV, so rho is 1.3. The area is twice the area of one cylinder, and the area of that cylinder is pi r square, pi r square because it's a circle, and then the velocity is 1.8 meters per second. Another way you can also think about this is basically I have found using rho v the mass that flows through in 1 second, right? Because this is a mass per unit time in a way, so this is just the mass flowing in 1 second. So the density multiplied by the volume in 1 second, this is the area corresponding to that circle, and in 1 second it would cover this length of 1.8 meter according to what the speed means, right? And then because I need the mass in a time interval of 2 seconds, so delta m would be whatever this answer is, just multiplied by 82, and this turns out to be 0.030 kg. Next part, calculate the increase in momentum of the mass of the air in B1. So increase in momentum, so it was initially stationary, right? The air was initially stationary. So I know that the change in momentum corresponding to this mass would be mv minus mu, so it's just mv, which is 0.030 times its final velocity, which I guess was 1.8. So this turns out to be 0.054 Newton second. Force exerted on this mass by the propeller. So if I have the change in momentum, all I need to do is divide it by the time to get the force. So 0.054, the time was 2 seconds. So this value now turns out to be 0.027. Explain how Newton's third law applies to the movement of the air by the propeller. And this is something that should have also been immediately obvious when you started looking at this question. So you can say that basically the propeller pushes, or the car pushes the air backwards, so the air pushes the car forwards. And you also know now that Newton's third law and conservation of momentum are basically the same thing. So if asked that way, you should have been able to explain this in terms of momentum as well. Anyway, here I'll just say this. So the force applied by the propeller on air is to the left. By Newton's third law, the air applies an equal force, and the magnitude of which I found above, for 2 seconds. So the air applies an equal force on the propeller to the right. Next, part 4, the total mass of the car is 0.2 kg. Brakes of the car are released and the car begins to move with an initial acceleration of 0.075 meter per second square. Determine the initial frictional force acting on the car. All right, so keep in mind that everything we're doing here is for 2 seconds, right? So if I need to find the frictional force, again I can say that it accelerates. So it accelerates with this force, which we just found was 0.027, and there's some friction which acts here. Obviously, if it accelerates, so the 0.027 is greater than F. So now I can figure out a Newton's second law equation for this. So 0.027 minus F equals ma, and the mass was given below with the acceleration. So 0.027 minus F equals 0.20 a. So F is 0.027 minus 0.20 times 0.075, which turns out to be 0.012 newtons. That was the first question. Now we'll be doing 2 more. This being another one. A jet of water hits a vertical wall at right angles as shown in 3.1. So this is a horizontal jet of water. Density is again given, velocity is given, cross-sectional area is given. Water hits the wall with a velocity of 5 in a horizontal direction. Cross-sectional area is given, density is given. Water runs down the wall after hitting it. Show that over a time of 1.6 seconds, the mass of water hitting the wall is 1.2 kg. Again, not very difficult because we've done that previous part as well. So I can find the mass flow rate easily, which is rho a v, right? Rho being the density, which is 1000, area 1.5 into 10 to the negative 4, and the velocity, which is 5. Being the mass flow rate, this is the mass flowing in 1 second. So for 1.6 seconds, I would need to multiply all of this by 1.6, and then the answer must be 1.2 kg. All right, part B now. So in part B, it says the decrease in horizontal momentum of the mass of the water in air due to hitting the wall. So mass of the water I found, there is some initial momentum here. Just a minute. Yeah. So there is some initial momentum here, but finally it basically runs down the wall. So horizontally, there's no final momentum. Horizontally, the momentum becomes 0. And it also says the decrease in horizontal momentum, right? So all I need to do is basically use the change in momentum formula. Final momentum is 0. Initial momentum is what you'll have to calculate. So 0 minus 1.2 times whatever the initial velocity was, which was 5. So I'm pretty sure this is 6 Newton per second. Newton second. Magnitude of the horizontal force exerted on the water by the wall. We also did that previous part. So you know that the force exerted by the wall on the water is equal to the force exerted on the wall by the water, right? So F equals delta P over delta T again, right? So that is 6, and this took place over a time of 1.6 seconds. So 6 over 1.6, this turns out to be 3.8 Newton. Part C, state and explain the magnitude of the horizontal force exerted on the wall by the water. All right, so if I'm thinking about this beforehand, things become really easy for me. So this is asking for on the wall by the water, and this was on the water by the wall, and it just says magnitude, so I'll say this is equal because of Newton's third law. Calculate the pressure exerted on the wall by the water. So pressure, even though we haven't studied this yet, but this is an O-level concept. Pressure equals force over area. So force I found, and it basically hits that same area because this is kind of like sticking to it, right? So there's no gap, so water can't like follow a projectile motion out of here. So force and area is 1.5 into 10 to the negative 4. So 3.8 over 1.5 into 10 to the negative 4. So this value turns out to be 2.5 into 10 to the 4 pascals. Now on to the last question related to mass flow rate. Pretty similar question, and hopefully inshallah this time you will be able to do this on your own. Winter 19, paper 21, question 3. A small remote controlled model has two propellers, each of diameter 16 centimeters, right? So diameter is given, and basically you can see this tracing out a cylinder as well, right? Air is propelled vertically downwards by each propeller so that the aircraft hovers at a fixed position. So obviously there's the weight of the aircraft which acts downwards. For it to hover at a fixed position, the propellers must exert overall an equal force upwards. Density of the air is given. Assume that air from each propeller moves with a constant speed of 7.6 meters per second in a uniform cylinder of diameter 16 centimeters. Also assume that the air above each propeller is stationary. Show that in a time interval of 3 seconds, mass of air propelled downwards by one propeller is 0.55. Alright, again the same thing. Mass flow rate, which is delta M over delta T, which is given by this expression rho AV, right? So rho being 1.2, A is for one propeller. So basically the radius is half of this, right? So if this is 16 centimeters, so the radius is 8, but it's also centimeters. Also, I'm wondering why the questions are kind of messed up. Anyway, that's a discussion for a later day. So pi into the length, which is 8 centimeters, so 0.08 squared into v, which is 7.6. Again, this is just for 1 second. So for 3 seconds, I'll just have to multiply this by 3. Very straightforward. And now we are eventually getting the hang of this idea. And this should give you 0.55 kg. Now the questions start looking really similar. Calculate the increase in momentum of the mass of the air in A. So air was initially stationary, so delta P is PF minus PI, with PI being 0, so it's just PF. So the mass is 0.55, the speed is 7.6, so this turns out to be 4.2 Newton second. Downward force exerted on this mass of the air by the propeller. So downward force F equals delta P over delta T. So 4.2 is delta P. Delta T is time interval, which is 3, which I think is 1.4 Newton. C1s, the upward force acting on one of the propeller, right? So this is what the force exerted on the air by the propeller, because that was the change in momentum of the air, so the force is also on the air. Now it's asking me for the force on the propeller, which would also be 1.4 Newton by Newton's third law, and the name of the law that explains the relationship between the force in B2 and C1, that is Newton's third law. Determine the mass of the aircraft. Okay, so the mass of the aircraft must be what? There is this upward force on the propeller, which is 1.4. There would also be this force on the other propeller. So 1.4, 1.4. Since this is an equilibrium, it's hovering. So it's basically at rest. So total force upwards equals total force downwards, right? Resultant force is 0. So that is 1.4 plus 1.4. That is the weight basically, which is 2.8, and for the mass that would be 2.8 divided by 9.81 by W equals mg. So that turns out to be 0.29 kg. In order for the aircraft to travel at a very high altitude, propellers must propel the air downwards with a greater speed than when the aircraft hovers at a low altitude. Suggest the reason for this. Now, suggest is something you need to think about. So it says that basically for it to hover, that means that the mass flow rate and the force must be the same. So why should the speed increase? That's because air thins out at high altitudes, so the density decreases, so the speed must then increase to compensate for the density. So density of air decreases with altitude. All right, and let's skip this part because this is Doppler effect, which we have not done yet. All right, so that was another video. In this we just discussed mass flow rate questions. Inshallah, in the days to come, I'll also be uploading more videos on elastic and elastic collisions, and specifically questions related to the 2D conservation of momentum. So like this video, comment if you have any questions or suggestions, subscribe to the channel, and I'll see you in the next video. Bye.